Welcome to AI Paperslop, the YouTube series where we summarize AI and tech papers for ML engineers and AI researchers. Today, we are tearing into a paper titled Why Large Language Models Fail at Tabular Prediction by Marta Garnello and Wojciech M. Zarnecki.
Yeah, and this is a really fascinating one.
It really is. And I'm just going to give you all the core insights right now so we can jump straight in. Generic LLMs fundamentally suck at tabular data prediction. And, it's not for the reasons practitioners usually think.
Right. It's definitely not what you'd expect.
Exactly. I mean, it's not because of CSV formatting, it's not numeric tokenization, and it's not random noise. The paper actually proves that LLM failure is strictly tied to dimensionality.
Which is such a wild finding.
Yeah, like in 2D feature spaces, an LLM acts almost exactly like a local distance-based classifier, like a Gaussian process or something. But as the number of features scales, that capability just completely dissolves into random guessing.
And it dissolves in this really bizarre way that no classical machine learning model mimics, even when you augment those classical models with noise.
Right. And furthermore, their chain of thought explanations for their predictions are basically just largely unfaithful hallucinations.
Yeah, that really sums up the existential crisis of applying LLMs to spreadsheets perfectly. I mean, the community has spent, the last year desperately trying to prompt engineer their way out of this problem?
Oh, easily a year. Yeah.
Because everyone just assumes that if the model is, smart enough to write Python code, it must be smart enough to run a simple logistic regression in its head. But this paper just systematically dismantles that assumption.
Completely tears apart.
Yeah. So the researchers looked at frontier models, specifically Claude Opus 4.6, and also Quen, just to ensure this wasn't like a single architecture quirk. And they tested them in what they call a pure inference regime.
Okay, let's actually define that pure inference regime for you as you're building these systems, because it's crucial for understanding the evaluation. This basically means no training wheels.
Right, zero training wheels.
Just a single prompt containing the full train and test data, no agents, no retrieval augmented generation, no code execution environment, and absolutely zero fine-tuning.
Yeah, the prompt is literally just, here's the data, predict the missing labels.
Which forces the model to rely entirely on its internal weights
and
its in-context attention mechanisms, right?
Exactly. So they gathered 19 standard tabular data sets to feed into this setup. We're talking about the absolute classics here from scikit-learn and the UCI repository.
Oh, yeah, like iris, wine,
breast cancer.
Sonar, yeah. The foundational data sets you'd use to test literally any new machine learning algorithm. But before they could actually measure performance, they had to run this contamination check, which they called a memorization probe.
Which is so important because evaluating an LLM on public data is always just a complete minefield.
It really is.
You have to prove the model is actually performing, geometric reasoning in its context window, rather than just regurgitating a data set it saw 10,000 times during pre-training. Right, and the way they tested this is actually quite clever. For each data set, they took all the rows corresponding to one specific target class and completely removed them from the training context provided in the prompt.
Okay.
So they trained the model in context on the remaining classes, but then asked it to predict the held-out rows in the test set.
So it's kind of like a teacher giving a multiple-choice test where the answer C has been completely scrubbed from the textbook, the lectures, the study guide, everything.
Yeah, exactly like that.
And if you are genuinely learning the material purely from the provided context, you should never, ever guess C. Like, you literally have no conceptual representation of C.
Precisely. A genuine in-context learner should score a flat 0% on predicting those original labels because the data simply isn't there to learn from.
Right.
And when the researchers ran this control test on classical baselines, like random forests or gradient boosting, every single one of them scored 0 by mathematical design.
But the LLM didn't score 0, did it?
No, it absolutely did not.
It perfectly recovered the original labels for the breast cancer and iris datasets. And it substantially recovered the labels for bank and wine, too.
Yeah, it just circumvented the prompt entirely. Even with the class missing from the context window, the LLM just dipped into its pre-trained parameter weights, recognized the statistical fingerprint of the features, and effectively just said, I know this is the iris dataset. The missing label is versicolor.
Wow. which is exactly why those specific datasets had to be completely thrown out of the study.
They had to go, yeah.
I mean, if a model already knows the decision boundary by heart, its accuracy isn't demonstrating in context learning at all. It's just data contamination masquerading as a capability.
Exactly. So they had to scrub the memorized sets to maintain strict scientific hygiene, and that left them with a clean set of 11 datasets.
Okay, 11 untouched datasets. And this is where the paper shifts into a bit of a detective story, which I love.
It really is.
They systematically dismantle the 4 most common excuses, the practitioner folklore, basically, for why LLMs fail at tables. So let's start with the first suspect, which is separability.
Right, separability.
The working theory here is that tabular data classes are just too noisy. Like, the data points overlap too much in the feature space for an attention-based model to draw a clean boundary.
Which, I mean, it makes intuitive sense, right? Language models are trained to predict the most likely next token in a probabilistic sequence. They aren't really trained to draw hard hyperplanes through messy, overlapping data points.
Right, totally different task.
Yeah. So the researchers artificially shifted the data. They took one of the classes and literally translated it step by step through the feature space until the classes were 100% cleanly separated. Zero overlap. A perfectly clean boundary.
So if the issue is just noise and overlap, giving it a perfectly clean gap should make the LLM's accuracy just absolutely skyrocket.
You definitely expect a massive jump. And the classical baselines, like logistic regression, they saw immediate and massive spikes in performance.
But the LLM.
The LLM barely registered the change.
Yeah.
Even with fully separated classes, it still completely failed to master the task.
Wow.
Yeah, so the failure is clearly not about the data being too noisy or inseparable.
Okay, so we can confidently cross separability off the suspect list. Which brings us to the second excuse. And this is the one you see debated endlessly on, engineering forums. Serialization format.
Oh, yeah, the classic CSV debate.
Right. The argument is that flattening a two-dimensional grid into a one-dimensional text string like a CSV just destroys the spatial structure. You're forcing a transformer's attention heads to jump across hundreds of tokens just to compare 2 values in the same column.
Right, and to test if the model was actually losing the column structure in the text format, they ran a literal needle in the haystack test.
I love this test.
It's brilliant. They took the target label, the actual answer, and embedded it as one of the feature columns in the prompt for both the training and the test rows.
So they literally gave it the answer key hidden inside the table.
Exactly. They hid it among up to 60 distractor columns. Now, if the CSV serialization format was blinding the model to the column structure, the model would fail to isolate that specific feature across the rows. It wouldn't be able to track the vertical alignment.
Makes sense.
But the LLM effortlessly located the designated column and copied the labels perfectly, even when it was swimming in a 60-dimension haystack. It can read and track the flattened CSV format without any loss of signal.
Okay, wait, I have to pause and push back on that for a second, because if the LLM's attention mechanism can reliably pull the exact needle out of a 60-dimension haystack, like if it can isolate and track that specific column perfectly down the page, why on earth can't it just perform basic math on those same columns to make a prediction?
And that discrepancy is the crux of the entire paper. The machine learning community has treated this tabular failure as a formatting bottleneck, a parsing issue or a context window problem.
Right.
But the needle in the haystack test proves the model parses the data perfectly. It attends to the correct column flawlessly.
So it's not the parsing.
Exactly. The bottleneck isn't parsing the data. The bottleneck is the geometric synthesis of that data. The model can read the numbers, but it cannot combine them to reason about the shape of the data. Parsing simply does not equal reasoning.
That is a staggering distinction. Okay, so format is out. Let's move to the third excuse, which is numeric tokenization.
Right.
Because if you look under the hood of a tokenizer like byte pair encoding, it absolutely butchers continuous decimals. I mean, a number like 3.14159 might get split into 3 completely unrelated token chunks.
Oh, it's a total nightmare for continuous math, so the hypothesis is very sound.
Yeah. So the theory is that these weird variable length token sequences bloat the context window and basically destroy the model's ability to compare magnitudes.
Yeah, and to isolate this, the researchers manipulated the decimal precision. They rounded the features in the datasets to 1, 4, and 8 decimal places.
Okay.
If tokenization chaos was the culprit, reducing the numbers to a single decimal place should drastically clean up the token sequences and, improve performance.
But I'm guessing the performance didn't actually change at all.
A completely flat trend line. The numeric precision of the tokens and the resulting length of the token sequences was totally irrelevant to the failure.
Okay, scratch tokenization then. So that leaves the final piece of folklore, which is per-query test load. This is the idea that if you ask the model to predict 100 test rows at the end of a single prompt, it's just spreading its computational budget too thin across the generation phase.
Right, because for a conventional ML model, batching your test queries doesn't change the underlying classifier at all.
Right.
But for an autoregressive LLM, generating a long sequence of predictions might degrade the context or deplete the hidden states. So they chunked the test set, they asked for half the predictions per prompt, then a quarter, then just a handful.
And if the generation load was the problem, asking for fewer labels at a time should absolutely rescue the performance.
But it didn't. The trend line was entirely flat again. Asking it for a single prediction versus 100 predictions yielded the exact same terrible accuracy.
Wow. So we have systematically eliminated class overlap, CSV serialization, decimal tokenization, and test batch size. Like none of the things we constantly tweak in our pipelines actually matter here.
Nope, none of it.
Which finally brings us to the true culprit. The researchers proved the bottleneck is dimensionality collapse.
Yes, and this is where the paper moves from debunking myths to exposing a really fundamental architectural flaw. The researchers took the datasets and applied random linear projections across powers of 2.
Okay.
So they swept the data from 1 dimension to 2 to 4, 8, 16, all the way up to 64 dimensions.
Okay, we definitely need to unpack what a random linear projection actually does mechanically for the audience. Because they are mathematically transforming the data into higher dimensions, but they aren't destroying the underlying information, right?
Exactly.
They're just sort of rotating and stretching it across more axes.
Think of it like taking a signal and broadcasting it across multiple channels. The information necessary to classify the data is fully preserved. The only thing that changes is the number of features, the number of columns the model has to simultaneously process to reconstruct that signal. A learning algorithm that scales properly mathematically should have no problem retrieving the signal, regardless of how many columns it is spread across.
And when you feed these multi-channel, higher dimensional projections into the classical baselines, the random forests, the gradient-boosted trees, the logistic regressions, what happens?
Well, every single classical baseline either maintained its performance or actually improved as the dimensions grew. They're fundamentally designed to utilize distributed signals across multiple columns.
But the LLM collapses.
The LLM was the only method that suffered a catastrophic downward trend. By the time the data was projected into roughly 16 dimensions, the LLM's normalized score sank to the equivalent of blindly guessing the majority class.
Wow.
Yeah, the geometric reasoning just completely dissolved.
But let me play the skeptic here for a second, because this is where you have to be careful about real-world data. Couldn't it just be that the real tabular data sets they were projecting have hidden, noisy correlations that just blow up and become toxic when you mathematically project them into 64 dimensions?
And that is the exact skepticism a rigorous researcher should apply. So to control for that, they built a synthetic experiment.
Oh, nice.
They took perfectly solvable two-dimensional synthetic data sets. We're talking simple geometric shapes like moons, spirals, and checkerboards. Visually and mathematically trivial tasks.
Okay, so the core data is fundamentally simple.
Very simple. Then they upscaled those 2D synthetic data sets to 64 dimensions using random matrices. And here is the critical part. Mathematically, the data still lives strictly on a simple 2D manifold.
Okay, let's give a visual for that.
Yeah.
So imagine you have a flat two-dimensional piece of paper with a drawing on it. That's your simple data. Now, crumple that paper up and toss it into the middle of a massive 64-dimensional room. It's taking up space in all 64 dimensions. But if you trace the surface of the paper, the drawing itself is still mathematically just 2D. The researchers essentially did that.
That is a perfect analogy. The data was wearing a 64-column trench coat, but underneath, it was just the simple 2D moons dataset. And the result. Every classical baseline recognized the underlying 2D shape and remained flat or improved, but the LLM still rapidly deteriorated.
Unbelievable.
Yeah, the underlying pattern was simple, the manifold was simple, but merely forcing the attention mechanism to look at the extra columns caused the computation to shatter. It is strictly the dimensionality that breaks the LLM.
It is like the model has a hard RAM limit on how many simultaneous variables it can juggle in a geometric space before its internal representation just gives up entirely.
Exactly.
But we know high dimensions break it. It sort of begs the question, though, when the LLM actually does work, like when it successfully solves those low-dimension 2D tasks, what algorithm is actually manifesting inside its neural weights?
Right. And to figure out what the LLM is secretly doing when it succeeds, they ran a massive behavioral profiling experiment.
Okay.
They took 252 uniquely configured classical models, support vector machines, multi-layer perceptrons, decision trees, naive Bayes, you name it. And they compared their exact decision boundaries against the LLM's predictions on those 2D synthetic tasks.
So they are basically treating the LLM's predictions like a fingerprint at a crime scene and running it through a database of known machine learning algorithms to find a match.
That's exactly it. And in 2D space, they found an incredibly clear match. The LLM behaves almost identically to a local distance-based classifier.
Meaning it's looking at a test point and simply asking, what are the training points closest to me, this geometric space?
Yeah, the closest algorithmic matches in the database were a Gaussian process using a Matern kernel or a low nearest neighbors model.
Oh, wow.
Essentially, algorithms that map localized pockets of probability based on how close data points are to each other. These classical models match the LLM's predictions on 91 to 92% of the grid space.
That is highly correlated.
Very. When you overlay their decision boundaries visually, they draw the exact same broad regions, really only disagreeing slightly near the highly ambiguous edges.
So in 2 dimensions, this trillion-parameter cutting-edge language model is mostly just doing sophisticated nearest neighbors.
Basically. Yeah.
But the high-dimensional mystery is what really fascinates me. What happens to that algorithmic fingerprint when you push the LLM past its 16-dimension breaking point?
In high dimensions, the LLM completely alienates itself. They ran the exact same database comparison against the 252 classical baselines on the higher dimensional datasets. The closest classical model only agreed with the LLM 64.8% of the time.
That is a massive drop from 92%. I mean, it's an alien failure mode.
Right.
It's not just failing, it's failing in a way that no known mathematical model in their entire library replicates.
Yeah, it doesn't look like a failing random forest. It doesn't look like a failing support vector machine. It doesn't look like a failing Gaussian process.
But wait, if an LLM is struggling in higher dimensions, couldn't it just be acting like a noisy version of a classical model? Like maybe it's still trying to compute a Gaussian process, but the 64 dimensions are just injecting static into its attention heads, causing it to randomly guess the majority class sometimes.
They tested that exact hypothesis. They mathematically crippled all 252 classical baselines by injecting dimension-dependent random noise into them.
Okay.
They really wanted to see if they could reproduce the LLM's specific pattern of failure by taking a standard classifier and randomly replacing its predictions with noise.
And did crippling the baselines with noise help match the LLM's fingerprint?
Scarcely at all. Tuning the noise model for every single baseline barely budged the agreement score by 0.5%.
Less than 1% improvement.
Yeah, which means this high-dimensional failure cannot be explained by taking a standard classifier and degrading it. The LLM's geometric reasoning capability dissolves in a highly specific structural way that no noise-corrupted classical learner mimics.
That is wild.
It is a massive open question for mechanistic interpretability. We know the computation dissolves as dimensions scale, but we have absolutely no idea how the geometry shatters inside the transformer architecture.
So if we can't mathematically reverse engineer its high-dimensional behavior using our standard ML toolbox, the natural instinct for any engineer using an LLM is to just ask it, right?
Of course.
I mean, these are language models. You can just prompt it. Explain your reasoning step by step. Give me the mathematical rule you use.
Well, you can certainly ask it, but as the researchers proved, it will absolutely lie to you.
The illusion of reasoning.
Mm-hmm.
Walk us through how they tested this, because this is dangerous territory for practitioners relying on logs.
It really is. So on the 20 simple 2D tasks, they prompted the LLM to output a text explanation and a definitive mathematical rule for its predictions alongside the actual predictions themselves.
Okay.
You get the answers, and you get the chain of thought logic it supposedly used to arrive at those answers.
Which sounds incredibly useful for debugging.
It does sound useful, but out of 20 tasks, it only got both the predictions and the explanation right 6 times.
A 30% success rate on explaining itself on trivial 2D shapes. That is terrible.
And it gets much more concerning. In 4 of the tasks, the LLM's predictions were highly accurate and perfectly matched the geometric data. but the stated rule it generated in text was completely wrong.
Right.
Yeah. It gave a highly plausible sounding explanation that drew a decision boundary entirely different from the one it actually used to make its accurate predictions.
That is a severe faithfulness gap. The transformer did the math right implicitly in its hidden states, but when forced to verbalize that math into text tokens, it just hallucinated a rule that sounded smart.
Exactly. And in the remaining 10 tasks, so that's half of the entire 2D suite, both the predictions and the text explanation were completely decoupled from the ground truth. Neither matched the data, and they didn't even match each other.
This is such a critical warning for you as you integrate these models into your pipelines, because LLMs sound incredibly convincing when they output a chain of thought explanation.
Oh, they sound so confident.
They use bullet points, they use confident language, they write out the mathematical boundaries as if they are definitively referencing their own computation.
You absolutely have to treat LLM self-explanations on tabular data as diagnostic artifacts. They are text generation decoupled from the predictive mechanism. Do not take an LLM's explanation of a tabular dataset at face value, ever.
Absolutely. Well, let's bring this theoretical deep dive back to the physical day-to-day reality of running these systems. If we step back from the accuracy charts and look at the sheer logistics, running an LLM directly on a real-world table is absurdly unscalable.
It is entirely unfeasible in production. Let's just do the token math really quick.
Yeah, let's do it.
A tiny 100,000-row dataset with 20 numeric columns contains 2 million individual future values. At roughly 8 input tokens per serialized CSV value, a single prompt containing that train and test set would consume about 16 million input tokens.
16 million tokens for one prompt. I mean, that completely blows past the largest context windows we have today, unless you're aggressively chunking or heavily downsampling your data.
Right. And even if you could fit it into a future model, think of the compute cost.
Oh, man.
At $5 per million tokens, you're looking at $80 per inference attempt.
Huh.
The tiny toy-scale experiments in this paper alone cost the researchers nearly $1,000 in API credits just in input tokens, solely to prove that the model fails.
$1,000 just to prove it doesn't work. So what is the actionable takeaway for the ML engineer listening to this who just got handed a messy tabular dataset?
Basically, stop trying to force a square peg into a round hole. Stop trying to prompt engineer your way out of tabular prediction problems.
Yeah.
Stop tweaking the CSV format. Start playing with decimal precision, and absolutely stop relying on chain of thought to fix the accuracy. Generic LLMs are just the wrong tool for this modality.
Use the right tool for the job.
Exactly. If you want to use modern deep learning architecture, look into purpose-built tabular foundation model systems like Nexus or TabPFN.
Right.
These are transformers designed specifically from the ground up for the tabular modality, or frankly, just stick to the classics. XGBoost, random forests, gradient-boosted trees. They cost a fraction of a cent to run, they train in seconds, and they will obliterate an LLM on a multidimensional table.
It's a humbling reality check, isn't it? The most advanced autoregressive systems on the planet, systems that can pass the bar exam and write complex software architecture, consistently lose to algorithms developed decades ago the moment they face a standard spreadsheet.
It really highlights the fundamental architectural difference between language processing and geometric reasoning.
Which leaves me with a final lingering question for you to mull over. We've seen today that LLMs fundamentally fail at higher dimensional geometric synthesis, even though the attention mechanism can read and parse the underlying data perfectly.
Right.
So if an LLM cannot balance 16 simple numeric columns without its internal logic collapsing into random guessing, how can we trust them to balance 16 interconnected logic variables in an advanced coding environment or a complex physics problem?
Wow, yeah.
If the capacity for synthesis dissolves with dimension in a simple structured table, where else is that reasoning dissolving right beneath our noses in unstructured text?
That is the exact question researchers probing the limits of autoregressive reasoning need to be asking right now.
Definitely something to keep in mind the next time you paste a massive data set into a chat window expecting a miracle. That's all for today's discussion on the source material. Thanks for tuning in to AI Paper Slop, and we'll see you next time.